Hello, everyone, and welcome to this NSDI talk titled When to Hedge in Interactive Services. My name is Mia, and this work was completed during my PhD at EPFL with the help of my advisors, Professor Katerina Argyraki and Professor Edouard Bugnion. We evaluated when and how it makes sense to use hedging in noisy data center environments. What is hedging? It is a technique that reduces latency by sending redundant requests. We focused on so-called online data-intensive services. Web search and advertising are some of them. Now let's see why these services are called that way. Online is basically just another name for an interactive service, which means we have users that send a request and expect an immediate reply. If this does not happen, the user might become impatient and abandon the service. This delay has two main components: network latency and data center latency. In this work, we focus on a subset of interactions happening inside the data center. Now, let's zoom in and see where this request got stuck. But first, let me explain the data-intensive part. Each of these requests has to query a large amount of data that does not fit into a memory of a single machine. Therefore, this data is split and shared across so-called leaf nodes. Then we have the root or the dispatcher node that is scheduling this request or split into queries to each of these shards, like that. All of these queries have to finish for good accuracy of the results before the request can complete. But something happened on shard number 1, and this query got stalled, therefore the request was not able to complete. So we can say that the request completion time is lower bounded by the slowest of these queries. This is becoming a problem with a big number of shards because the probability of something going wrong on at least one of them increases proportionally. This is the so-called tailored scale problem. So why is it that some queries finish faster than others? As we all know, queries come in bursts, and then sometimes some of them will experience additional queuing delays. Then we have the service time that is very likely to vary. But some components of the service time, we understand why it varies. This is the predictable component of the service time, P. For example, a range query will always take longer than a simple lookup query. Then we have the unpredictable component of the service time that we call intra-query service time variability, IQ jitter or J for short. Let me clarify what I mean by that. Let's say we have the same shard, A, replicated twice. Query Q, which is the same query, starts on both of them simultaneously. Something happened on the right-hand side shard. Maybe this was the bad operating system scheduling decision, or maybe a power management algorithm kicked in, or there was another application that was competing for CPU or cache resources on the same machine. Many things could have happened, and the other query just finished sooner. Researchers have been trying to tackle each and every source of IQ jitter, and this is a very difficult problem. It might take a long time to eliminate each and every one of these sources of latency variability. So what can we do if we want to live with IQ jitter? How can one be scheduling queries knowing that IQ jitter exists? We can ignore it and just do load balancing as we've always been doing, in two main ways: push-based load balancing with distributed queues and pull-based load balancing with a centralized queue per shard or per shard queuing. The latter is optimal when network latency is negligible, which we know from queuing theory. Then we can try to tackle IQ jitter by doing hedging. Hedging will mitigate the effects of IQ jitter, but it will increase the system load. Let me show you the simplest possible hedging policy there is. When the request comes in, two queries are sent to identical replicas of the same shard. One of them finishes, and the request was able to complete, even though the other query was still stuck over there. To build some intuition for the trade-off between hedging and load balancing, we ran many discrete event simulations. Here I will show you one of them. So we have 50 shards, each of them replicated twice. We will model P as an exponential, and we will assume that once every 1,000 queries, something happens, which is not related to query processing itself, and there is going to be a slowdown, a hiccup of 15 times the average P. For more details, please check the paper. Now let's look at some graphs. On x-axis, we have utilization, and on y-axis, we have 99% latency as a multiple of P. I'm showing you the simple hedging policy and the per shard queuing, which is the best load balancing policy in this case, because our network latencies are negligible. We can see that at low loads, naive hedging manages to achieve much lower latency. However, the throughput of load balancing, of per shard load balancing, is much higher, and because the other policy is simply saturating the system with all these redundant requests. If only we could have the low load of naive hedge, the low latency of naive hedge, while keeping the high throughput of per shard queuing. Exactly like this. We call this policy Idealizat, and now let's see how we designed it. So it has two main properties. There is 1 queue per shard, like in per shard queuing, and its properties are work conservation with redundancy, which means that a worker node is never idle if it can serve some useful replicated query. Then we have prioritization of new or duplicated queries, which means that when two replicas are running, two query replicas are running, and a new request comes in, then its query can replace one of these two. Which one? The perfect predictor of query completion times will decide that, and it will eliminate the one that is going to finish later in time. This perfect predictor is the idealized part about this idealized hedge. In our setup, we can say that if idealized hedge does not yield benefits on a certain workload, no realistic hedging policy will do so either. Now, let's see how using idealized hedge, we can evaluate when hedging is a good idea. I'm showing you the same graph from before, and I only kept two of the lines. The area between per shard queuing and idealized hedge is the potential of hedging. So for example, above 60% utilization on this graph, we can see that hedging doesn't make sense anymore. We ran many such simulations, and we did sensitivity analysis on how the potential of hedging changes with cluster sizes and different hiccup distributions. For more details, please check the paper. Now, a natural question arises, which is how close to idealized hedge can one get in practice? We studied different state-of-the-art policies, and the best one we found is this one. It's called delayed hedge with cleanup cancellations, DHedge for short. And it works as follows. After the delay D, which is a parameter that we tuned and optimized, a replica query is sent to the other shard replica. And after one of them is finished, the other one is cleaned up using these cleanup cancellations. As you can see, there is still some space to improve the performance of DHedge and get closer to idealized hedge. So can we do that? Our answer to this question is load-aware hedge, or LÆDGE for short. It has similar properties like idealized hedge, and we implemented 3 variants of LÆDGE. No cancellations, with cleanup cancellations, and with both cleanup and preemptive cancellations. What is good about LÆDGE compared to the state-of-the-art is that it does not require any parameter tuning. Now let's see how it works. I added LÆDGE and LÆDGE with cleanup cancellations on the graph that we saw before. And you can see 2 things. First, both LÆDGE and LÆDGE with cleanup cancellations manage to close this gap towards idealized hedge. We get closer than the best of the existing policies. Second thing we can see from this graph is that the 2 lines are pretty close to each other. Therefore, these cancellations do not add a lot of extra latency benefits. Of course, we implemented this in a real system and evaluated in AWS. We used as code base Google's online data-intensive framework, OLDI SIM, and we implemented our policies inside it. We ran this on 10 virtual machines, so we have 5 shards replicated twice. As an application, we used Lucene that we trained on English Wikipedia. Now let's look at our system results. On x-axis, we have queries per second, and on y-axis, we have 99% latency in milliseconds. I'm showing you naive Hedge that we saw before, a push-based load balancing called random load balancing, a pull-based load balancing, which is per shard queuing, and our LÆDGE policy without cancellations. The benefit of LÆDGE compared to per shard queuing is on average 49% in this area that I shaded on the graph. What we saw is that our system results closely match our simulation, and this is despite having these realistic latencies between our virtual machines. For more details, please check the paper. You can also find more information about the benefits of Idealizat Hedge and LÆDGE with added number of replicas. So actually the potential of hedging increases as we add more replicas. Then, of course, this can scale to any number of shards using many routes and many per shard load balancers. Also, we did sensitivity analysis or different parameters and analyzed how the potential of hedging changes. And finally, we have this LÆDGE with cleanup cancellations and preemptive cancellations, which is very sensitive to the accuracy of this preemption. And you can see analysis on that in the paper. There are three main things I'd like you to take away from this paper. First, there is a trade-off between hedging and load balancing. And because of that, there are many realistic scenarios for which hedging simply doesn't make sense. What one should do instead is proper load balancing. Second, we saw that there are also many cases in which cancellations don't add a lot of benefits. Since they are pretty challenging to implement, these are good news for application developers. And finally, we saw that pull-based policies can outperform push-based ones in a real system. And with that, I would like to thank you for your attention, and I'm looking forward to your questions. Thank you very much.